Hola, mis estudiantes de químicos. Welcome to day 63. Should be digging out your ETD to ETD 63, where we're going to target things like how do you make a solution with an exact concentration in at least two ways. I know, it's going to be exciting. When we proceed into this, of course, lovely picture, one of my favorite Easter memories. It's one big Lego morph. Hasenpfeffer. Here's what we're going to go after today, of course. They're going to get rid of my big, ugly head. This is a beautiful place called Lake Nyos in Cameroon in West Africa. And one of the things we should notice about it is it's not that pretty. That's because it's stuck in the middle of a rainforest. There's a lot of erosion that goes into the lake, and it's up in the mountain region, so the sides erode really fast because they're steep. And it looks a lot like the top of a volcano, because it is. Now, this is, of course, a caldera volcano that filled in with water, so it's a volcanic caldera, and it's an active volcano. But people didn't really recognize that because this lush soil and everything. They built a huge village south of it. The only problem is one thing that bubbles out of volcanoes is, of course, carbon dioxide. So that essentially got trapped in the bottom of the lake, and the lake is so deep because it's a huge caldera that it like a soda, it held it under pressure at the bottom layers of it. But then a problem happened. If you take a bottle of soda and you shake it, and then you open up the top, then all the gas escapes really fast. And that's essentially what happened when there was an earthquake. The layers inside the lake helped it stay isolated, and then that earthquake caused a landslide that fell into it. That, of course, agitated the CO2. It came out, and being more dense to the air, it flooded down to where all the villages were. And there's lots of villages because volcanic soil is good for growing stuff. If you've ever had pineapples from Hawaii, you know that. Now, as it did that, it did it in the middle of the night, and it flooded over the village, and unfortunately for the villagers, they never woke up from their slumber. Here's, of course, you can see their goat herds and stuff, and the people sadly died inside the huts because they were smothered by the cloud of CO2. There was no oxygen for them there. Just a little bit of, gas not liking to be in solution because, of course, it doesn't like to be in there because it's non-polar. Why do I bring this up? It killed, 1,700 people because this is a sparsely populated area compared to other places like where you find other volcanic lakes and calderas. But scientists recognized that they didn't want this to happen again, so the government in Cameroon actually hired some scientists to come along, and what they did was they basically did what you do with soda. They put a giant straw in it, and that giant straw was able to go down to the lower layers and seep off the CO2 and bubble it out, and there's the geyser right there, letting it out in small increments so it couldn't build up because it was that landslide that agitated it so quickly to come out. So they degassed it, and that means the people there could, of course, come back to their farms. So hopefully they'll never run into a problem like that again. This should hopefully ring a bell when you live near volcanoes, like, say, you live in the Pacific Northwest, or you go off to this great place called Yellowstone Lake in the middle of Yellowstone National Park, where that's another big caldera with a giant lake on top of it. And it's also bubbling out throughout. That's all the hot springs and the great mirror pool, reflecting pools that are there. Or you head south down to the Bend area and you can find Crater Lake. Crater Lake, of course, blew its top off a long time ago, but it's on our string of volcanoes. So it's still bubbling out gases, and it's likely that it probably has some trapped at the deep levels of this. That, of course, is a bigger deal because a lot more than 1,700 people live at the base of it. That beautiful valley in Bend could be right there. So one thing we can notice is I was thinking about creating my own soda called Crater Lake Soda. Not even the caffeine will wake you up. Or I like this one. It's the cavities that kill. All you got to do is shake it up and let the top off, just like Nyos. And I know, sick humor, but it's not Shasta Cola. It's Crater Lake Cola. Now, that should freak you out if you, say, live 50 miles from a giant volcano that's, linked to it. But fortunately, there isn't a lake at the top of it. It's just a whole bunch of ice that can melt really fast. Oh, that's a concern because as the gases like sulfur dioxide and CO2 bubble out of this, they destabilize and actually react with the rocks that are inside of it. That's why whole sides of it fall off, like this side that fell off and made the valley of Enumclaw. So it's all down to gas solubility. That's why our volcanoes are exciting around here. Now, today what we're going to go into, not that it has anything to do with real life, it's just chemistry. What we're going to go into, of course, is starting off with dilutions and how you figure those things out. And probably the most important question that I ever ask a new hire at our school, and if they can't pass it, is B, because we make solutions a lot. You're not only going to figure out how to make it, you're going to explain what are the steps to make it. If you can do that, then you can work on my team. Many people have failed it. So write down the questions, give them a swing on your own, see if you can handle them, and then in a millisecond, we will do them together. So pause me. Cool. If we look at this, A shouldn't be too bad considering what we did last time. All you got to do is ask yourself what you got and what you need. And what you need here is it wants to know what would be the new molarity. So that should tell you that we're looking for an M2. Also, you can recognize that you've got some stuff. You've got 125 milliliters of a 0.2 molar hydrobromic acid solution. And then if you've got 150 milliliters of water that are added to it, so you're watering it down, that's a dilution. And anytime there's a dilution, you should say to yourself, hey, I got the solution. It's M1V1 is equal to M2V2. Our unknown for this is the new molarity, so that's M2, right? And then I can plug in my knowns and hopefully solve this thing. M1 would be the original solution of 0.2 molar, 20 molar hydrobromic acid, right? The volume that you had of that was the 125 milliliters you're starting with, right? That's your stock solution. Then we want to know the new concentration that we'd have, and we added 150 milliliters of water to it, so that means that we'd have to take the 150 milliliters of water and add that to the 125 that already existed, right? That would give you the whopping 275 milliliters. That's your new volume, your V2. And then you'd use some algebra and you'd solve for your M2 by dividing both sides by 275. That would give you a molarity of 0.091 molar hydrobromic acid. And the pen's freaking out, right? Thing that we should recognize, that number makes sense because what you started off with, of course, was you had 125 milliliters of that sample, and that had its own concentration of 0.20 molar. I'll put like 2/10 of a pile in there. Then what you did to that was you took that solution and you added to it more than twice the amount. You raised it up another 150 milliliters of solvent to bring it up to 275 milliliters, added on to the 125 that was there, but you didn't add any solute. So that's going to spread it out, and that's going to make it like, well, for every half of that, it's like your half is concentrated, a little bit less. That's, well, 0.091 molar, which is less than half, but pretty close to half because you watered it down more than that, right? The numbers always make sense if you think about what's going on, and you draw the piles inside the solutions. I highly suggest if you're ever stuck, you do that. Now, the more important question is B. And B is important because this is what chemists have to do all the time. This is what I have to do anytime I set up a lab for you, whether it's in this class or a future class, right? You want to make 10 milliliters of this solution. The only solution that you have is a stronger solution of a 0.4. So obviously one thing you're going to do is you're going to take your stronger stuff, your stock we call it, and you're going to dilute it. So you start off with a dilution, right? And that means that we're going to need to know how much of it that we actually use. So step one is going to be to calculate your V1, how much of your strong stuff. So you're going to use your M1V1 is equal to M2V2, right? Your starting off concentrations of strong stuff, that's the 0.4 molar of whatever this stuff is. And you don't know how much of it you're going to use because you want to use a little bit of the strong stuff, not all of it. That, of course, is the goal of getting you a new molarity, and that's the new molarity that's right here. That's your M2 of the weaker solution, the 0.10 molar solution. That means that you want at the end of this exactly this amount, which is the 10 milliliters of that solution. That's what you're shooting for. That's what I always make. I'm making mine in 2 liters and stuff like that. So when I do that, of course, I can use my algebra. I can solve for V1 by dividing both sides by 0.4, and you come up with 2.5 milliliters. And a lot of people on test day will be like, bam, there's my answer. But that's not the answer. That means that you're going to use 2.5 milliliters of the 0.40 molar solution. That is still at the concentration of 0.40. So that's not giving me what I want, right? So that means that if I draw this, I can think about it. What I want to do here is I started off with a solution, and I had 10 milliliters of that stuff, right? If I use just 2.5 milliliters of it, that's like 1/4. So imagine each part of it has a 0.4 of a pile in it. That would give me my 2.5 milliliters of that, or 1/4 of that solution. Now I'm going to transfer that to another beaker. When I transfer that to the other beaker, I'm just going to pour it in there. There it is. It's got my mini moles, my tenths of a mole. It's in there, but that's still the 0.40 molar solution. So step one, you find out your V1. Step two, you pour off your V1 of your stock into another beaker, right? Then when I do that, I got to water this thing down, and I want to bring it to exactly 10 milliliters. So I'm going to add to it 7.5 milliliters of water. Now, when I do that, that means that in step three is I add solvents. And I'm going to add the solvent, which is the 7.5 milliliters of it, to bring it to V2. That's my new volume. And my new volume goal was at the end of this, 7.5 plus 2.5 is 10 milliliters, 10 milliliters of it. But now that solute that you didn't add in the second step, that solute now it's got a beautiful thing. In the last step of this, now it's watered down with a solvent, and now it's going to be, 0.1 molar because you've now watered it down by adding 7.5 milliliters. The cool thing is now my concentration is actually at, the concentration I wanted, my M2. So we should notice that the key of this is not the answer. The answer was, you want to know how you do this. What you would do is you would combine 2.5 milliliters of your strong 0.40 molar solution and 7.5 milliliters of water, and that would give you exactly 10 milliliters of the 0.10 molar solution, 1/4 of that stuff. That's the answer that we would be looking for. You'd have to figure out how to do it, and that's the question. Now, if you can't do that, you can't be a chemist on my crew or in any chemistry crew, because we make solutions all the time and they have to be the exact right solution. And typically the way that we do it is we water it down. The other way that I could make it is, instead of starting with a stock solution, I could start with the solid and then I could add the solution to that. But the tricky thing is I recognize the solid also takes up space. So I always fill it up to my target volume, because that allows the fact that the other stuff that you put in, whether it's a solid or the original solution, is going to take up space. You always add water afterwards, right? Cool. You can also look at my PowerPoint slides to see a clearer way of seeing this, but hopefully it takes you through it. Now, typically we look at the new solutions worksheet and talk about Johnny and Hank and stuff. They're on your new sheet. What we're going to do instead, of course, is not take the beautiful break with this little tater puff sitting there in the grass. What we're going to look at is the idea of, can you add concentrations? And a lot of people are like, well, I got a 5 molar solution. I have a 1 molar solution. Can I make them together and have a 6 molar solution? So we do this thing with test tubes with dye. And you can do this one at home. It's perfectly safe. And try it out. Here's the basic idea of it. We would have 3 different test tubes. In A, you would take some dye and you would put in 4 drops of dye. And that 4 drops would be in 20 milliliters of water. Now, the neat thing about it is those 4 drops, we can fake like they're moles, right? If we divide that in half, that means in every 10 milliliters, there's exactly, of course, 2 drops. So if we simplify that, that's 4 to 20, which is the same as 1 to 5. We could call that like 0.2 dropolarity, right? It's like molarity, but it's fake, right? Then, of course, we had another beaker. In that other beaker, we put only 2 drops into it. We're going to add this to it. Those 2 drops is going to 20 milliliters of water again. So that's 2 to 10. That's 1/10. So that would have 0.1 dropolarity, fake molarity, right? That means when I look at this solution B, because this is my A, inside of B, there would be 1 drop in every 10 milliliters of it. It's got, half as much dropolarity to it. So then if I take those numbers and I combine together, I got a 0.2 dropolarity for A, and I got a 0.1 dropolarity for B. Well, can't I just add those together and get C? A combination if I take half of each of those. And that would give me like 0.3 dropolarity for C, right? No, that's not how it works. You can't just add concentrations. And when I do this, I have to recognize what's going on. If I was to take half of A and half of B and pour them in and make a 20 milliliter solution, what I'd have, of course, is I'd have A, and every half of A has the 2 drops, right? When I pour it out, I don't change its concentration. Then I would add half of B, and when I do that, it only gets, of course, its concentration to 0.1. I'm not only adding solute, I'm also adding solvent, which increases the solution's volume. Hey, I'm diluting it, right? That means that total, what I have is I have 3 drops of solute in 20 milliliters. And what that means, that's 3 to 20, that's a 0.15 dropolarity for C. And that's a big deal, because that means that, that is actually not going to be 0.3. It's much less concentrated because I diluted A and I made B more concentrated. So try that model at home and figure it out and see if you can solve that one. Now, get out your notes while I hide my kids away. Go upstairs. That's hence all the screaming and yelling and giggling. Now, key things, of course, we got to go into in this one is molarity and stoichiometry. So this is a nice step into it. Stoich's been around for a while, but remember that Stoich's main goal is to change from one substance to another. So write down the question, pause it, and try to solve it, right? Now, key thing we should always recognize is you figure out what you got and what you need. To do that, you probably want to have yourself a nice chemical reaction. So write down the chemical reaction as well. Hey, look, it's the old switcheroo, a double replacement precipitation reaction. Now, what it's asking me to do is to calculate the number of grams of the solid that's formed. Right? That's my target. So at the end of this, I should have grams of silver chloride. And with that, of course, I got to figure out what I got. And what I got here is I got a bunch of things. Benny, go upstairs. Yay, there we go, reality. They figured out how to unlock the door. If we look at this, of course, we got a couple of things in here. One of the things I can notice is this is liters. That can be handy. And this is molarity. Now, which one do I start with? I'm going to start with the one that contains moles. And molarity contains moles. So that's a big hint for you. Now, when I do this, of course, I'm going to recognize that it's 0.200 moles of silver sulfate in every 1 liter. Always write it as moles per liter, and life's easier. Then I'm going to use the power of dimensional analysis. Now, the next thing I should notice is when I change this thing, I don't have a full liter of it. I only have 0.4 liters of it, not even a half a liter. That, of course, is going to allow me to get rid of liters because I can say, okay, in my one sample, I've got 0.40 liters. That's cool because that's going to turn it just into moles. And as soon as you see moles, you're like, ooh, I could take that and turn it into any substance. Now, this is for my reactant, silver sulfate, but I want to change it into my product, silver chloride. So I'm going to use my mole to mole ratio. When I do that, I'm going to kill off the silver sulfate, the reactant, and turn it into my product, silver chloride, right? When I need to do that, of course, I've got a nice balanced equation. Always double check it. Looks good and balanced. When I notice here is what I've got is one of those for every 2 of those. So this is a 2-to-1 ratio, reactant to product, right? Then, of course, the next step is that would kill off the moles of the silver sulfate. I got to turn it into grams. Hey, a G thing. I'm going to get rid of moles of silver chloride and turn that into grams of silver chloride. That's what your periodic table is for. 1 pile of that, if you add it up, is 143.32 grams of silver chloride. Now, the good news is moles and moles cancels. And now I'm in grams of the right substance. I'm in the right unit, right? When you throw that into your calculator, you notice you started with 3 siggy figgies. So you end with 3 siggy figgies and you come out with 22.9 grams of silver chloride. Now, I ask myself, does that number make sense? Well, silver chloride is relatively heavy, and I'm not using a whole lot of grams of it, but that makes sense because I started off with a pretty dilute solution at 0.2. Notice this is a lot like Stoich that we've done before. The only new trick is recognizing that the piles that you're using are starting in a solution. So the key is to you've got that solution, use your number of liters to cancel out the solution, which will just leave behind the piles, because the piles are just floating around in the solution. Once again, check the PowerPoint for a clear view of it, but that's the basic steps of it. Now, the good news is you'd be going after a Stoichs and solution worksheet. Some of those questions have been transferred to the one that you're doing for your COVID vacation. So that, of course, should be what you should be able to attack now as you go into that part. Normally, we'd be doing that and then figuring out how you can't add concentrations. You'd have to figure out that you're both adding solute and solvent. So you're going to dilute one and make one more concentrated when you add those things together. So you actually have to look at the amount of solute or solvent. And if we're going to make a solution with a concentration we absolutely want to know the concentration of, and easy ways to do it is M1 over V1, dilute it. Start with a stock solution, water it down. Or you can start with a solid and figure out how many grams of that solid you need, turn those into piles, then put that over liters, and bam, you got yourself a solution. Either way is handy, and that's typically what you use. Hope that was helpful. I'm going to go see what the monkeys are up to upstairs. All right.